Okay, well, there's really not much left. It all has to do with stability for solving systems of ODEs. I'm not sure if I will uh, cover everything that's in this document today. If not, certainly then it will be all done on Tuesday. Then there'll be nothing left to deal with except y'all finishing a homework and then and dealing with the oral finals. So hopefully soon I'll be hearing from you about the timing of that. Okay, now let's see. And as far as how things are scheduled, I like to have a 1 hour time slot. That doesn't necessarily mean I'm going to grill you for an hour, but I just want that much time to set aside. In case I'm gonna do like 2 or 3 of these in a row, but I don't want them like bumping into each other. Okay. Now I'm gonna check on, as I've said a few times, that the key source here is the notes. I'm looking through them real quick. What's going on here? That's weird. I opened up the notes file and it was blank. And now it's not blank. Not sure what happened there. Okay. I want to see if I can possibly narrow things down a bit. Okay. All right, so we have 5 chapters in total. And I'm finding various things that I would like to possibly ask questions about. But I've also found some things that could be excluded. Okay. For example, in chapter 1, the last few sections, I'm going to cut out because those really deal more with the kind of things you'd know for a theoretical PDE's course as opposed to a numerical one. Okay, and then certain topics within those chapters of interest. Classification of PDEs. Okay, well posedness. Classical versus weak solutions. Okay. And dispersion relations. All right. Okay. Chapter 2 is on finite difference. There was one section in the middle of that chapter I did not cover. That was 2.3, so forget about that. Okay. All right. So topics of interest there, find different stencils, how to handle boundary conditions, the unholy trinity of convergence concepts, consistency, stability, convergence. Okay. And items related to that. Okay. All right, and then there's chapter 3. There's only 2 sections in chapter 3. One on periodic boundary conditions where you use Fourier series, and then non-periodic where you use Chebyshev. So either of those could come up. Okay. All right, chapter 4. All right, I was on linear systems. Okay. And yeah, there are some cases where I might exclude a topic simply because I don't feel like talking about it, or asking something about it. Okay, directives. Preconditioning. Okay, for chapter 4, the subsection of 4.2 preconditioning is of interest, and also 4.3, which is on the stationary iterative methods. Like multi-grid, what's the main idea behind multi-grid? Okay. 4x4 on grid of subspace. Although it's a little difficult to think of fitting questions from this stuff. But I should not rule it out entirely. Yeah. We'll see how it goes. Okay. And then finally, chapter 5 on ODEs. Okay, well, anything from there's a possibility at least. Although, Okay, as far as the kinds of questions, all right. All right, so now I need to make a disclaimer here. It's not meant to be an exhaustive list. And I can have a situation where like Well, you didn't say that's a question like that. These are the kind of things that could come to mind as things that I'm most likely to ask about. We've seen a lot of methods for different situations. In some cases, you may have a choice of method. What makes you choose one option over another? Okay. Okay. Certain definitions. Example: what does it mean for a problem to be well posed? What is meant by what? How is consistency different from convergence? Because there are some similarities in those definitions. Okay. How are methods categorized? Like, what does it mean for a time-stepping method to be, explicit versus implicit? Okay. One thing that came up, a question that I got. So based on that, for example, what if I showed you a, excuse me, Runge-Kutta method, and I gave you its tableau? Could you write out what the method is, or vice versa? So like, how do you go back and forth? That's something that came to mind. Okay. What is the certain key properties? For example, what is the order of accuracy of Euler or trapezoidal rule, or an Adams-Bashforth method? What's the order of accuracy of four-folded Runge-Kutta? You better get that one right if I ask it. So. Okay. All right, just to give you an idea. Yeah. All right. Questions about any of this?
Not from me.
Okay. Or any of you, ever 5 of you?
What date is the exam like? What date do you have in mind? Is it going to be final exam week that would set a specific schedule, or it could be any time after this class is over?
Oh, yeah. So that's up to you. I mean, okay. The last day to do this would be Friday of finals week, Friday, December 10th.
So it could be tomorrow.
I like my light Fridays. Please, not tomorrow. Anytime after that, we'll talk.
Okay.
Any other?
Do we have class the week before finals?
Good question, because actually a little while ago I was thinking about that, because because of also having class a Tuesday before Thanksgiving, I will definitely have everything covered before Thanksgiving from the notes. So at that point, I guess there's really no reason to have class. I mean, because y'all can come to me at any time with any remaining homework issues. So yeah, let's just agree to that now. That there will not be class during dead week. At this rate, I feel like because we'll all be dead. At least mentally. All right. Well, at least my Tuesdays and Thursdays have just gotten lighter. Anything more? Okay. Let's see how things go getting through these notes. All right. So what's happening here is that we have, as we've been dealing with in this chapter, some linear ODE, something like du dt equals LU for some operator L, and then you perform spatial discretization, for example, using finite difference or spectral methods for the spatial derivatives, and then you wind up with this system of ODEs. A lot of times this system of ODEs might have a source term, but for now we'll just deal with something of this form that comes from, and that this is what you would get from any of the fundamental PDEs we've been dealing with, like like heat equation or wave equation if it's rewritten as a first order system. Okay, so we know what the exact solution of this is. E to the AT times the initial data. So any numerical method is going to try to approximate this in some way. Now, I guess kind of unfortunate, the term stability is going to be used in two different ways in this topic. The focus is on stability of numerical methods, but stability also applies to analytical solutions of ODEs or systems of ODEs, and basically requiring that the solution exhibits physical behavior, that if the eigenvalues of A have negative real parts, then the solution is said to be stable, because what's going to happen is as t goes to infinity, the solution is going to go to 0. We don't want to have a situation where the solution grows over time. We certainly don't want that, because that's something that would not happen in any physical phenomena you're modeling. You hope anyway. So when it happens, if the eigenvalues have strictly negative real parts, then the eigenvalues of the exponential will be less than 1 in absolute value. So then the solution is shrinking over time. So that's what we're going for. And the idea is that numerical methods should just should produce solutions that exhibit that same behavior. So if we take a look at forward or explicit Euler for a system of linear ODEs like this one, then this is how you get the solution at the new time from the old time. All you're doing is you're multiplying by identity plus delta TA, whereas with implicit Euler, you're multiplying by this. And we see here, these are the first two terms of a Taylor series for e to the a delta t. So this makes sense as an approximation. Here we have the first two terms in the Taylor series for e to the minus a delta t, but then you're taking the inverse of that, so this whole thing is also approximating e to the a delta t. So so a lot of methods are like this, where you're just multiplying by your previous solution by some matrix, and that matrix is meant to approximate the exponentials. So for a numerical method to be stable, then the eigenvalues of this matrix must be less than 1 in absolute value. So we want the eigenvalues of this matrix M to mimic this property of the eigenvalues of the exact solution operator. Okay. So if we know the eigenvalues of A, then the eigenvalues of M in this case are easy to get, because M is itself a function of A. So these are the eigenvalues of M in the case of forward Euler. So these are required to be less than 1 in absolute value. So if we set this to be less than 1, then that means this quantity has to be contained in a disk in a complex plane, where the center is located at -1, the radius is 1. So, so in other words, these have to be pretty small in order to have a solution behave reasonably. So that's why we say that explicit Euler is conditionally stable, because you can't just choose any delta t you want. It has to be chosen small enough relative to the eigenvalues of A, so that this whole expression has absolute value less than 1. So. Let's see. Okay. I will be able to. I will have an example of that shortly. On the other hand, if you look at implicit Euler, here are the eigenvalues of M in this case. That you're taking 1 minus delta t eigenvalues of A, but then M in implicit Euler case is, where'd it go? An inverse matrix. So then you're taking 1 over the eigenvalues of this. So that's where we get the eigenvalues of M in this case. Now, keep in mind, A has eigenvalues that have negative real parts. So what happens here is the real part of this expression, this denominator, is going to be strictly greater than 1. And then you might have some imaginary part also. The point is, the denominator is going to be greater than 1 in absolute value. So therefore, the eigenvalues of M are going to be strictly less than 1 in absolute value, no matter how you choose delta t. So that's why implicit Euler's said to be unconditionally stable. So that's what we really want. There are unconditionally stable methods, but very few methods have that property. And when they do, it's implicit methods that have that. And implicit methods have their downsides, because they require more work per time step than generally than explicit methods do. And that's what I was just mentioning here, that oh, whoops, that's wrong. Time step of an implicit method is more expensive. So yes, I was just saying explicit is more expensive than explicit. Whoops. Okay. So there's a trade-off. That even though each time step of an implicit method is more work, you're able to take fewer time steps because you can get away with a larger time step. And in many cases, if you consider the total amount of time to compute the solution, that an implicit method will give you an advantage. So that's the key there, is not just work per time step, but also how many of those steps are you taking. Okay. Actually, I was looking at this earlier. I think, yeah, there's a mistake here in this solution. The minus should be right here. So here we have a system of ODEs with this, so y prime is AY, and here's the initial data. This matrix, if you were to go ahead and compute the eigenvalues, like using eigen, or it can be done by hand, the eigenvalues turn out to be -1 and -99. So that's what leads to these exponents that we get. So take into account the initial data. This is the exact solution. And this is an example of a stiff system of ODEs, because we have the two eigenvalues that are very different in magnitude. So if you were to plot this solution And then if you were also to plot just this part, like you were to neglect the second term, for most part, except maybe at t near t equals 0, you would find them to be very similar, because with the e to the minus 99t, this term decays to 0 very rapidly. So you might think, well, since that term is so small that it should not really impact a numerical method. Unfortunately, it does. That because of its large but negative eigenvalue, you have a severe time step restriction to guarantee that explicit Euler would be stable. And I will work through the algebra on that now. Okay. Okay. All right, so we need this inequality to be satisfied where m is equal to identity plus delta t a. So we need to have absolute value 1 plus delta t lambda I, where lambda 1 is equal to minus 1 and lambda 2 is equal to minus 99. So if we get rid of the absolute values, so we have minus 1 less than 1 plus, okay, 1 minus delta t less than 1. So this is for a case of the first eigenvalue being equal to minus 1. And we have minus 1 less than 1 minus 99 delta t. Okay. So now I want to simplify these. I'm going to add 1 to all sides. Okay. Now, in each case, the second inequality is automatically going to be satisfied just because delta t is always positive. So this part is not worth looking at. It's the other inequality that we need to pay attention to. So, okay. Well, just for completeness sake, we'll have, okay, so from a first eigenvalue of minus 1, we get delta t must be between 0 and 2. Not a big deal. But from here, we have delta t must be between 0 and 2 over 99. So delta t must be less than roughly like 0.02. So okay. So this is what happens with explicit Euler, that the more spread out the eigenvalues are of your matrix, the more severe the time step restriction will be. Okay. So if you choose delta t outside of this, if you choose it too large, then this solution, which is supposed to decay over time, would end up actually growing. So, questions about this? Okay. Next example, we have like ut equals uxx. So one-dimensional heat equation, and we use a standard difference for uxx. Then we're dealing with this matrix A, and we're assuming Dirichlet boundary conditions. And the eigenvalues of this matrix can actually be computed. So it can be shown that the spectral radius of A, so the magnitude of its largest eigenvalue, the eigenvalues will be negative, but the magnitude will be less than 4 over delta x squared. So it'll approach this upper limit here. And what happens is, all right, so we have real eigenvalues because A is symmetric, and so what happens is, from the eigenvalues, 4 over delta x squared, we fill that in here. This is your matrix. These are this comes from a matrix M, identity plus A delta T. So we work through the same kind of inequality like I was doing up here. Then this is the stability condition you get. The delta T must be bounded above by delta x squared over 2. So this is an incredibly severe time step restriction because now delta T is proportional to delta x squared, whereas for the wave equation, stability restriction would be delta T being proportional to just plain delta x. But because it's squared and delta x is already going to 0, as you square it, then this small value gets much smaller, so delta T has to be really small. So that's terribly impractical, and that's why one would generally prefer not to use forward Euler, explicit Euler for the heat equation. So for such problems, implicit methods are generally preferred. And here's an example of one of these implicit methods. It's called the Crank-Nicholson method, which is actually based on the trapezoidal rule. So what you're doing is you take your solution from a previous time step, you perform this matrix vector multiplication to get the right-hand side of a system of linear equations. Basically, it's an AX equals B problem, and this is your matrix that you're inverting to figure out yn plus 1. Excuse me. So here we have like an explicit part over half a time step, and an implicit part over the other half of a time step. And it turns out that it can be shown that that this method is unconditionally stable. Because when you have lambda being a negative real number, then this fraction that comes from these matrices here, actually need to include delta T. Okay, this fraction can be shown to be less than 1 in absolute value. And the reason for that is because lambda is a negative real number, then that makes this denominator larger than what we have here. So it can also be shown that as delta T gets larger, then this fraction actually converges to -1, and it converges from below. So it still satisfies this inequality. So because this is true regardless of delta t, that's how we get Craig-Nicholson being unconditionally stable. Now, but if you choose delta t too large, then what we have is certain eigenvalues of A, or not A, M, converting to -1. Because what happens is basically the solution gets negated each time step. It's jumping around, which is not something that you would expect to see in nature. Certainly, heat diffusion would not behave that way. So even if, for the sake of stability, you're able to choose literally as large as the delta t's you want, that can cause other problems. So that's just something to be mindful of. Okay. Okay, questions about this example? Okay. Here we actually have this. This is the very, very last section of a note. Now, way back in chapter 2 of finite difference chapter for time-independent problems like Poisson's equation, where we first looked at consistency, stability, convergence, and the Lax equivalence theorem. It says that if a scheme is consistent and stable, then it's also convergent. And the way you would figure out consistency is you do Taylor expansion to get a hold of the local truncation error, and then check whether that goes to 0. And then stability is a bit harder to come by. That depends on what method is being used. In Poisson's equation, we're solving an AX equals B problem, and you want to make sure that the eigenvalues of the inverse could be bounded as spacing delta x goes to 0. Here I show you another way of checking stability by assuming that the initial data has this form, e to the ikx, so basically a wave from a Fourier series. So substituting it into a PDE and seeing how the solution at the new time either grows or shrinks from the solution at the previous time. So I'll show you how this works. So here's your heat equation. So we just go ahead and use e to the ikx for the initial data. And for the heat equation, we're not dealing with boundary conditions or anything like that. We know what the exact solution is supposed to be. Basically, e to the ikx, and you're multiplying it by e to the minus d. D is a diffusion coefficient. K squared t, where k is the frequency of your wave. So your exact solution is just a multiple of your initial data, and this multiple is called the growth factor. And we want to make sure that the growth factor does not exceed 1, because we're trying to model physical phenomena. We want physical behavior. We don't want our solutions growing over time. So here we have a growth factor of the exact solution what we want to do is get the growth factor of the numerical method and check, is it bounded by 1 in magnitude, or over certain cases where it might not be. So as an example, if we solve a heat equation using a explicit Euler in time, and then here we use central differencing in space for the UXX. So this describes the whole scheme. So then what you can do, well, first, just to simplify things, I've rearranged it that the solution at the new time is equal to all this, where we use a shorthand, R is capital D delta T over delta X squared, just to have a scheme in a simpler form. Now we go ahead and substitute, basically UJN is e to VI, e to VI KX. So we go ahead and substitute that in here, just on the right side, and this is what we get. And what happens is we're plugging in X values to the right and left of XJ. And okay, actually I need to fix my notation here. This should be XJ. So this is your solution from previous time evaluated at XJ. What are you multiplying by? This. So we want to make sure that this right here is a growth factor. But right now, we don't know if it's actually causing growth in the solution or is it being damped over time. Is it greater than 1 or is it less than or equal to 1 in magnitude? So we need to try to simplify this somehow, just as part in square brackets. So what we can get here is using certain trig identities, we get is the cosine introduced. So now to make sure of this, just by requiring this to be less than or equal to 1 and greater than or equal to minus 1, we end up with this inequality. And the thing is, we want to make sure that this is satisfied for all k. Now, the way that you can do that is you can replace cosine. You can replace cosine by a Taylor expansion. Okay, so let's take a closer look at this and what you see here. We also have to keep in mind what R is equal to. So I'm going to fill R in here. Okay. 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 Now, 1 minus cosine. Actually, you know what? I actually think I could do this without a okay. Yeah, I could do this without a Taylor expansion. Okay. So 1 minus cosine k delta x is the same as 2 sine squared. Okay. K delta x over 2. Actually, I'll be more specific. I'm working with a, or basically the inverse, or reverse of a half angle identity. That this is equal to this. Now this, of course, can be this could be no bigger than 1. So to make sure that this is satisfied, regardless of a value of k delta x, then we need 2 d delta t over delta x squared to be less than or equal to 1, which leads to this condition here. So that's where it comes from. Okay. So, so as we've seen before, it's conditionally stable. And this is the same condition we've seen before. This is just another way to obtain it. So questions about this one? All right. Here's von Neumann analysis for another scheme, Crank-Nicholson. So here we have a time derivative approximated using a forward difference again. But here we have 1/2 times uxx at time tn plus 1, corresponding to this, plus 1/2 uxx approximated at time tn. So we can see from the superscripts here. So now we want to make the same assumption about the form of a solution. And one thing that can make things easier algebra-wise is anytime you are changing grid points in time and space, it's always a multiple of e to the I kx. So, so you can think of ujn as being just equal to 1. And then if you go to the right on your grid, you have a factor of e to the I theta, because that's what e to the I kx will be multiplied by. The neighbor to the left, uj minus 1n, is e to the minus I theta, where theta is a shorthand for k delta x. If you're looking at anything at time tn plus 1, then the growth factor g is involved. So we can take these algebraic shortcuts, which could be figured out by looking more closely at what was done here. And when we make the substitutions, this is what we get. So see that here we have growth factor minus 1 over delta t, and then for these approximations of uxx, we'd have e to the I theta from this term and this term, e to the minus I theta from this term and this term. These middle terms would just be equal to minus 2, except for everything over here, because you're evaluating a time tn plus 1, you have to multiply by g. So that's what leads to this coming from a terms of time tn plus 1, this coming from a terms of time tn, and these are common to both. So then what you want to do is take this equation and solve it for g. So as a shorthand, we use the same definition for R that we did earlier. So R is d delta t over delta x squared. And that simplifies things a little bit. And now we can take this equation and solve it for G. So this is the growth factor. Now, R is positive, and this factor here is non-negative. So the denominator is always going to be greater than or equal to 1. It's going to turn out to be larger than the numerator. So it doesn't matter what the value of theta is. This growth factor is always going to be less than or equal to 1 in magnitude. So this method is unconditionally stable. Questions on this one? Is this the last one? Yes, this is the last one. Same idea, only 2 dimensions. So you meant to make an appropriate assumption for what the solution at the previous time looks like. E to the I kx and then plus ly to account for the second dimension. So you if you use the same finite difference scheme for uxx and uyy, central differencing in space, explicit Euler in time like before. So we have this same term on the left side, and then here we have so this is what we end up with when making all of the substitutions and using, for example, we have e to the ik delta x and then e to the minus ik delta x, which leads to the cosine here, and then a similar one over here. So if you start with this kind of expression for uxx, and then a similar one for uyy, and make this substitution throughout, then it simplifies to this. So then, well, as before, the goal is to solve for G, to try to find what the growth factor is. And what we have here is whatever we're subtracting things off. Like, okay, so this is non-negative, that's non-negative. They're multiplied by positive numbers. So it's just by inspection, we can see that this is at least less than or equal to 1, because there's always 1 minus something positive. But we also have to make sure that G is greater or equal to minus 1. So if we set this greater or equal to minus 1 and simplify as much as we can, then and try to make sure that this is satisfied regardless of a value of k delta x or L delta y, then we end up with this. So we end up with this stability condition. Oh, that's a mistake. That should be delta y squared. So this is very similar to the stability condition for the heat equation. Like in one dimension, we had this less than or equal to 1/2, but now we have this term to contend with also. So we make a simplification that if you're going to have square grid cells, so delta x equals delta y is equal to some common spacing h, then we have this condition on delta t. So delta t is proportional to the grid spacing squared, which again is a very unfortunate time-step restriction. So this is not a practical scheme to use. Okay. Questions about this? I've come to the end of a note, so I guess this means we don't have to have class on Tuesday. I figured you'd like that. Are there any homework questions? Is there anybody even there?
We're here.
Okay. Well, you know, I'm looking at 6 sore pictures. So.
Remember to keep the cameras off for when you record the notes.
Oh yeah. I guess that's particularly important for when I'm at the board. But yeah. Okay. I guess I won't be doing that anymore this semester.
So Tuesday there is or is not, like, is there no class or is it like office hours?
Well, I mean, I'm gonna be around anyway, but yeah, I mean,
No
we're not
class.
gonna be back in the classroom. Put it that way. So during that time slot, you can do what you want.
So I have a question on D. 5D.
5D. Okay. I'm gonna put that up. Okay, hold on. Okay, let's homework. Where to go? Okay, so Poisson periodic case, but part D.
Okay, so you said define f of x in 3 pieces. I didn't understand what you meant by that.
Oh. Okay, right. So the overall domain is from 0 to 2 pi.
Yeah.
So your first piece would be x. Okay. Yeah. X greater or equal to 0, less than pi over 2, where it's equal to -1. And then there'd be this middle piece from pi over 2 to 3 pi over 2. The second piece would be 1. And the third piece would be from 3 pi over 2 to 2 pi.
Okay. So that's when we want to find the exact solution. Do we do the same thing when we're trying to define f for the numerical solution?
Oh, it's not necessary in that case. Like what I would suggest is if you okay, in the code, if you do have a vector of x's defined, from 0 to 2 pi, then start by setting f equal to a vector of all minus 1s, and then you could use logical indexing like f
Okay.
of like x
It's greater than
1. Yeah.
okay. So can you explain this zero mean one last time for this one?
Okay. So what happens is, and so for both methods, that so you go ahead and set up the system equations. You have a u equals f problem. Not thinking about the zero mean at that time. But go ahead and get your solution, and what will happen is the solution that you get from backslash will be shifted by some constant factor just because of how MATLAB would handle solving a system with a singular matrix. So you're doing this as a post-processing stage. So once you have u from using backslash, doing this will give you the zero mean solution.
Yeah, so but how does it apply to D? That's what I was asking. Because here in part D, you said u of x must have a zero mean, so its integral over 0 to 2 pi must be 0. So we just
you're asking about the exact solution?
yeah, so we just integrate the exact solution from 0 to 2 pi and check that it's 0.
Yeah, so that would be one of your equations. Okay, so when you integrate this twice, because there are 3 pieces, you're going to have 6 total constants of integration. So then you'd have a system of 6 equations and 6 unknowns. Yeah, but okay, but then you have one more equation. So what you do is, since you have your 6 constants of integration are unknown, if you compute the integral of that from 0 to 2 pi, then even though it's a definite integral, your answer will not be a number, but it'll be some expression in terms of those 6 constants. And it'll be linear in them. So that would give you, and you set that equal to 0, that's going to get you a 7th linear equation in those constants of integration.
So, but why do we need 7 equations when 6 equations will still give us C?
Okay. Unfortunately, I don't remember what happened when I first worked this out myself. But I think what happened was when I set up a system using just the 6 conditions. Okay, so U periodic is a condition. Okay, U prime condition, and then continuity at the interfaces. That was not enough. Like, I think what happens is that system of 6 equations and 6 unknowns, I think it turned out to be singular.
Okay.
But I didn't bother to find out which equation was unnecessary. So then I went ahead and just formed a 7th equation. So even though it looks like it's a overdetermined system,
yeah,
you actually can get an exact solution, meaning that the residual is 0.
Okay.
And it's really a situation where, in general, that matrix, you would not be able to get a solution, but because the right-hand side is happens to be in the column space of a matrix, the system can be solved.
Okay. I noticed something on page 24 of the notes.
Okay.
This is 24. 23. Yeah, this notation you gave, it really confused me.
Where? Oh,
This dn, the differentiation matrix.
yeah.
So what does those arrows on top mean?
Okay, so in other words, I guess we're asking what is DN actually? How you form DN?
Yeah, so because I looked at this matrix and I tried forming dn from this what you have here, it turns out that wasn't dn. So I had to solve this u prime of xj for a 4x4 case to see what the matrix looked like. So I was confused, like, what does this notation mean? Maybe I didn't understand the notation. I was trying to form it from this notation you have for dn in matrix form. Or because in the real matrix, this was positive. The first element was 0, the next was positive 1/2. And here it's negative 1/2. So I don't know, maybe that's what this 3 vertical dots represent. I didn't understand what the notation meant.
Okay, so these are the entries on the various diagonals. So because this is what's known as a Topless Matrix, meaning that all the entries along any given diagonal are the same. So the entire main diagonal is 0. The entire first super diagonal is this, and so on.
So the entire first super diagonal is positive?
Yes. And the first subdiagonal is on negative. Or at least if it's coefficient, it's still a matter of what cotangent is. But now what you could always do instead of dealing with this, so this also gives you a formula for the entries. So if you ignore the part and you
yeah, sorry, that was the one I used to get the answer. Like,
yeah, okay, that would work.
Yeah, I see it now. I just didn't understand what this notation meant. So it was confusing for me. But like I worked out for a 4x4 and see what it looked like. And now that you're explaining it, it makes sense.
Okay.
Because I have the sub-diagonal to be negative 1/2. The first super diagonal to be positive 1/2. Okay.
All right.
I don't think I've seen this notation before.
Oh, okay.
Okay. Yeah, I think that's all for me.
All right. We have a very few minutes left. Anyone else? Okay. So no more class. Woo! But certainly, let me know of any homework difficulties. Let me know when you want to take the oral final, in the next couple weeks or so. And we'll get it all done.